Atlantic Ocean, March 1943. The freezing spray cuts across the deck of the merchant vessel SS Robert Rowan as she plows through 12-foot swells. Her captain grips the chart table, staring at a piece of paper that looks, frankly, ridiculous. A series of dots, circles, statistical probabilities, numbers that seem to have nothing to do with the life and death reality of submarine warfare. His first officer leans in, skeptical. "Sir, they want us to change our entire route based on this?" The captain nods slowly. "Orders from the Admiralty, something about operational analysis." "Operational what?" "I don't know, some scientist sitting in an office in Liverpool plotting dots on graph paper." Lahatam. What neither of them knew, what almost no one in the Allied navies understood at that moment, was that those boring dots, those tedious charts, those mind-numbing statistical calculations were about to turn the tide of the Battle of the Atlantic. A battle that Winston Churchill later said was the only thing that truly frightened him during the entire war. This is the story of how one man's obsession with data, with patterns invisible to the human eye, with what his critics called tedious number crunching, saved 3,000 merchant ships and potentially prevented Britain from starving into surrender. The Battle of the Atlantic wasn't like other battles of World War II. There were no clear front lines, no dramatic beach landings, no triumphant marches into liberated cities. Instead, it was a grinding, relentless war of attrition fought across 3,000 miles of cold, dark ocean. A war where victory was measured not in territory gained, but in tons of cargo that made it to port. By early 1942, Britain was in desperate trouble. The island nation imported more than half its food and nearly all the raw materials needed for its war industries. Every week, convoys of merchant ships had to cross the Atlantic, running a gauntlet of German U-boats that prowled beneath the waves like wolves hunting in packs. And the wolves were winning. In the first 3 months of 1942 alone, German submarines sank over 200 Allied merchant ships. That's more than 2 ships lost every single day. The mathematics were simple and terrifying. At this rate, Britain would run out of ships before Germany ran out of torpedoes. The British would be forced to negotiate, to surrender, to accept whatever terms Hitler dictated. Admiral Karl Dönitz, commander of the German U-boat fleet, had developed a strategy called Rudeltaktik, the Wolfpack tactic. Instead of submarines hunting alone, they coordinated in groups. When one U-boat spotted a convoy, it would radio the others. Soon a dozen submarines would converge on the helpless merchant ships, attacking from multiple angles, overwhelming the escorts. The Allied response followed centuries of naval tradition: more escorts, bigger guns, faster ships, aggressive captains who charged toward submarine contacts, dropping depth charges with abandon. It was warfare, as it had always been conducted: courage, aggression, and seamanship. It wasn't working. This is where our story's unlikely hero enters. His name was Patrick Blackett, and he was about as far from a typical military leader as you could imagine. No square jaw, no rows of medals, no inspirational speeches about duty and honor. Patrick Blackett was a physicist. 45 years old in 1942, thin, bespectacled, with a habit of chain smoking while he worked through complex mathematical problems. Before the war, he'd been researching cosmic rays at the University of Manchester, work so abstract that even other scientists sometimes struggled to understand its practical applications. But Blackett possessed something the military desperately needed, even if they didn't know it yet. He understood that behind the chaos of war, beneath the smoke and thunder and human drama, there were patterns. Mathematical patterns, statistical patterns, patterns that could be found, analyzed, and exploited. He'd started working on military problems in 1940, initially studying anti-aircraft fire. The question seemed simple: how do you shoot down an airplane? But Blackett approached it like a physicist approaches an experiment. He collected data, Hundreds of anti-aircraft engagements, thousands of shots fired. He analyzed the angles, the speeds, the distances, the weather conditions. What he discovered shocked the military establishment. Conventional wisdom said to paint anti-aircraft shells black so spotters could see them against the sky and correct the aim. Blackett's analysis proved this was completely wrong. Black shells were actually harder to spot. White shells, which seemed counterintuitive, were far more visible. Simply by changing the color of shells based on boring statistical analysis, anti-aircraft effectiveness increased by over 20%. It was a revelation, and it caught the attention of people at the highest levels of British command. In early 1942, Blackett was asked to form a special unit within the Royal Navy's Coastal Command. Not a combat unit, not an intelligence unit, an operational research section. His team would consist of 3 other scientists, a mathematician, and 2 junior officers to help with logistics. Their mission: use scientific analysis to improve anti-submarine warfare. The military brass were skeptical. What could a bunch of academics sitting in an office possibly teach experienced naval officers about hunting submarines? These scientists had never commanded a ship, never dropped a depth charge, never faced an enemy torpedo track racing toward their hull. Blackett's response was characteristically understated. "We're not here to teach seamanship. We're here to find patterns in the data." His team set up shop in a cramped office in Derby House, Liverpool, the headquarters of Western Approaches Command. The walls were soon covered with maps, charts, and graphs. They began requesting data: every convoy route, every submarine contact, every depth charge dropped, every ship lost, every ship saved. The naval officers who had to provide this information found it tedious, bureaucratic, a waste of time. After all, they had a war to fight. Why did these scientists need to know the exact time, position, weather conditions, moon phase, and sea state for every single encounter? Because, Blackett explained patiently, we can't see the patterns without complete data. The first major problem they tackled seemed unsolvable. The wolf pack attacks were devastating convoys. The standard naval response was to spread the escorts around the convoy in a protective screen, trying to cover as much area as possible. More coverage meant more protection, right? Blackett and his team started plotting the data. They mapped every convoy that had been attacked, the size of the convoy, the number of escorts, the position of those escorts, the number of ships lost. And they saw something that made no sense at first. Something that contradicted every instinct of experienced naval officers. Large convoys, with the same number of escorts as small convoys, were actually safer per ship. Think about that for a moment. It violated all logic. If you have 30 merchant ships instead of 15, surely you need more escorts to protect them. But the mathematics told a different story. The key insight was understanding the geometry of convoy protection. A convoy's perimeter, the area the escorts had to patrol, increased with the square root of the number of ships. But the number of ships increased linearly. So a convoy twice as large only had a perimeter about 40% larger. What did this mean in practical terms? A large convoy of 60 ships with 6 escorts had the same defensive coverage as a small convoy of 30 ships with 6 escorts. But the large convoy had twice as many targets. The U-boats attacking the same perimeter would sink roughly the same number of ships, but that number represented a much smaller percentage of the total. It gets better. Because convoys traveled together, a large convoy occupied the same patch of ocean as a small convoy. U-boats searching for targets had the same chance of finding either. But when they found a large convoy, even if they sank the same number of ships, the vast majority of the cargo got through. Blackett presented his findings to Admiral Sir Max Horton, Commander-in-Chief of Western Approaches. The recommendation was simple and radical. Combine smaller convoys into much larger ones. 90 ships, 100 ships, with the same number of escorts. The admirals were appalled. It went against every tactical doctrine. Large formations were unwieldy, hard to coordinate, created massive targets. One of the senior officers actually stood up and walked out of the briefing, but Horton, to his immense credit, studied the charts. He looked at the data, and he made the decision that commanders are paid to make. We'll try it. Start with the next convoy cycle. The results were immediate and dramatic. In the first month after the new policy was implemented, ship losses per convoy dropped by nearly 30%. Not because the convoys were better defended, not because the U-boats were less effective, simply because the mathematics of geometry and probability had been properly applied. 300 lives saved. Thousands of tons of cargo delivered, all because someone had taken the time to plot boring dots on graph paper and do the math. But Blackett was just getting started. The next problem seemed even more intractable. When escorts detected a submarine and attacked with depth charges, they almost never sank it. The success rate was abysmal, less than 5%. Naval doctrine, developed over decades, said to set depth charges to detonate at 150 feet. That's where submariners would dive when attacked, wasn't it? Deep to escape the blast? Blackett's team started collecting data again. Every depth charge attack, every setting used, every confirmed result. They even interviewed survivors from captured U-boat crews, asking detailed questions about their procedures during attacks. What they discovered was a revelation about human psychology and warfare. When a U-boat commander heard the splash of depth charges hitting the water, his instinct was to dive. Dive deep, dive fast, get away from the surface. 150 feet seemed like a safe depth, deep enough to escape, not so deep that it took forever to reach, using precious time while the explosions rained down above. But here's what the submariners didn't know, what their instinct prevented them from calculating in the heat of battle. Depth charges took time to sink, 9 seconds to reach 100 feet, 14 seconds to reach 150 feet. In those 14 seconds, even a submarine diving at maximum rate had only reached 70 to 90 feet. The depth charges, set to detonate at 150 feet, were exploding 50 to 80 feet below the submarines. Close enough to rattle the crew, to terrify them, to convince them they'd barely escaped, but not close enough to actually cause critical damage. Blackett's recommendation was simple. Set the depth charges to detonate at 35 feet, right where the submarines actually were during the critical first seconds of an attack. This time, the resistance was even fiercer. 35 feet? That was practically at the surface. Everyone knew submarines dove deep during attacks. Setting depth charges to shallow depths was wasting ammunition, wasting time, wasting effort. The submarine service itself opposed the change. Their own experience, their own training, their own survival instincts told them to dive deep. The idea that staying shallow was more dangerous seemed absurd. But again, Horton backed Blackett. A trial was ordered. 20 escorts would use the new 35-foot setting. 20 would continue with the traditional 150-foot setting. They would compare results over 3 months. The trial lasted exactly 6 weeks before it was canceled, not because it failed, because it succeeded so dramatically that it would have been criminal to continue letting half the escorts use the old settings. Escorts using 35-foot settings were achieving confirmed submarine damage or destruction in 7 out of 10 attacks, more than a 10-fold increase in effectiveness. U-boat crews who survived reported nightmare scenarios, depth charges that seemed to explode right on top of them before they could reach safety, boats forced to surface with damage, crews abandoning their vessels because the structural integrity was compromised. The word spread through the U-boat fleet. The hunters had suddenly become the hunted. Attacking a convoy was no longer a calculated risk. It was becoming a near-certain way to face devastating counterattack. 2 more examples will show you just how thorough, how obsessive, how brilliantly boring Blackett's approach was. Aircraft were being used to patrol the Atlantic, searching for submarines. When they spotted one on the surface, they would attack, trying to damage or sink it before it could dive. But the success rate was terrible. Less than 2% of air attacks resulted in confirmed U-boat destruction. The Air Ministry wanted more aircraft, more bombs, more patrols. Blackett wanted data. His team analyzed hundreds of air attacks. And they noticed something odd in the records. Aircraft painted dark blue or gray, the standard military camouflage, were spotting submarines at an average distance of 2 miles. But a few aircraft, through various flukes of maintenance and repair, had ended up painted white. Those white aircraft were spotting submarines at an average distance of nearly 4 miles. Why? The submarines posted lookouts. Those lookouts were scanning the sky for aircraft. A dark aircraft against a light sky was relatively easy to spot. The submarine would dive as soon as they saw it, often with enough time to submerge completely before the aircraft arrived. But a white aircraft against a light sky was much harder to see. By the time the lookout spotted it, it was too close. The submarine couldn't dive in time. Simply painting aircraft white increased successful attacks by over 30%. Then there was the question of convoy routes. Traditional naval thinking said to route convoys away from known U-boat concentrations. If intelligence reported submarines in a particular area, you sailed around it. Makes sense, right? But Blackett's analysis showed something counterintuitive. The Atlantic is huge. Really huge. Even with over 200 U-boats at sea, they occupied a tiny fraction of the total area. A U-boat could patrol for weeks without seeing anything. Their only hope of finding a convoy was if the convoy came close to them. By constantly changing routes to avoid reported U-boat positions, the convoys were actually helping the submarines. They were spreading out across the Atlantic, increasing the probability that some convoy would pass within detection range of some submarine. Blackett's recommendation was radical. Establish fixed convoy routes. Treat the Atlantic like a highway system. Yes, the Germans would learn these routes. But the mathematics showed that predictable routes through specific corridors, heavily patrolled by aircraft and escorts, resulted in fewer overall contacts than random routes across the entire ocean. It was like trying to hide in a crowd versus trying to hide by running randomly through an empty field. In the crowd, even though everyone knows where the crowd is, you're much harder to single out. Again, the naval officers were skeptical. Fixed routes seemed insane. But again, when they ran the numbers, when they actually tested it, the results were undeniable. Ship losses dropped. U-boat contacts in the convoy lanes decreased because there were fewer opportunities for random encounters in the vast, empty areas of the Atlantic. By mid-1943, all of these changes had been implemented. Larger convoys, shallow-set depth charges, white-painted aircraft, optimized patrol patterns, better training based on statistical analysis of what actually worked versus what seemed like it should work. The impact on the Battle of the Atlantic was staggering. In May 1943, the German U-boat fleet lost 41 submarines. 41 in a single month. Dönitz was forced to withdraw his boats from the North Atlantic entirely. The hunting grounds that had been so profitable for the wolf packs had become a graveyard. The merchant ship losses, which had peaked at over 100 ships per month in late 1942, dropped to less than 20 per month by mid-1943, and they kept dropping. By the end of the war, analysis estimates that Blackett's operational research group had directly contributed to the safe passage of over 3,000 merchant ships that would otherwise have been lost. 3,000 ships. Imagine that. Each one carrying food, weapons, fuel, raw materials. Each one crewed by 30 or 40 men who went home to their families instead of disappearing beneath the gray Atlantic waves. 30,000 sailors who didn't perish in the cold water. Millions of tons of cargo that reached Britain, keeping the island nation in the war, keeping the population fed, keeping the factories running. All because one man believed that warfare, beneath all its chaos and courage and tragedy, could be understood through mathematics, through pattern recognition, through boring, tedious, mind-numbing statistical analysis. But here's the deeper story, the part that makes this more than just a historical curiosity. Blackett wasn't just changing tactics. He was changing how wars would be fought forever. Before World War II, military decision-making was based on experience, intuition, and tradition. Generals and admirals made decisions based on their years of service, their understanding of doctrine, their read of the situation, and often they were right. Experience matters. Intuition can be powerful. Tradition exists for good reasons, but experience can also be misleading. Intuition can be wrong. Tradition can be outdated. And in the complexity of modern warfare, with thousands of variables interacting in unpredictable ways, the human brain simply cannot process all the information needed to make optimal decisions. That's what Blackett proved. Not that military officers were stupid, not that experience didn't matter, but that systematic scientific analysis of data could reveal truths that were invisible to even the most experienced commander. This approach, operational research, spread rapidly through the Allied militaries. The Americans adopted it enthusiastically. Teams of scientists were embedded with military units, analyzing everything from optimal bomb loads to the best tactics for island-hopping campaigns in the Pacific. The strategic bombing campaign against Germany was revolutionized by operational research. Early in the war, bombers were sent to hit precise targets: factories, rail yards, oil refineries. But the data showed that bomber crews, flying at night, under fire, in bad weather, almost never hit what they were aiming at. The bombs fell randomly across entire cities. Rather than admit failure, the operational research teams asked a different question. If the bombs are falling randomly, what targets should we aim for that would be most damaged by random distribution? The answer: cities themselves, worker housing, transportation hubs, the industrial capacity of entire regions. This led to area bombing, a controversial tactic that remains debated to this day. But from a purely operational standpoint, it was based on cold analysis of what bombing could actually achieve versus what planners wished it could achieve. In the Pacific, operational research determined the optimal depth for torpedoes, the best approach angles for attacks, the most effective patrol patterns for submarines. Every aspect of warfare was being analyzed, quantified, optimized. After the war, Blackett reflected on what his team had accomplished. He estimated that operational research had improved the overall effectiveness of Allied forces by approximately 15 to 20%. That might not sound like much. 15%. But in a war fought by millions of men with billions of dollars of equipment across every continent and ocean, a 15% improvement was the difference between victory and defeat. Think about that. Not some brilliant new weapon, not some daring strategy, just doing what you were already doing, but 15% more efficiently, making 15% fewer mistakes, losing 15% fewer ships, saving 15% more lives. Patrick Blackett received the Nobel Prize in Physics in 1948, though not for his war work. That remained classified for years. He returned to academia, continued his research into cosmic rays and particle physics. He was made a life peer, Baron Blackett, in recognition of his service to the nation. But his real legacy was something less tangible and more profound. He proved that science and mathematics could be applied to human conflict. That war, for all its human elements, could be studied systematically. That data and analysis were as important as courage and skill. Today, every military in the world has operational research divisions. Every major campaign is supported by analysts, statisticians, and computer scientists. The missiles that can strike within feet of their targets, the logistic systems that can supply armies thousands of miles from home, the intelligence analysis that can track terrorist networks across continents. All of it builds on the foundation that Blackett established. Ironically, Blackett himself was a complicated figure in the post-war world. He became increasingly left-wing politically, opposing nuclear weapons, criticizing American foreign policy, advocating for the Soviet Union in some contexts. Some of his former allies felt betrayed. The man who had helped defeat totalitarianism now seemed to be making excuses for it. But perhaps this, too, was consistent with his scientific worldview. He looked at the data of the Cold War, the nuclear arms race, the competition between superpowers, and he saw patterns that others didn't. Whether he was right or wrong in those analyses is still debated by historians. What's not debatable is his impact on World War II. The Battle of the Atlantic was the longest continuous military campaign of the entire war. From the first day of the conflict to the last, submarines and merchant ships fought across the ocean, and for the first 3 years, the submarines were winning. Then a physicist and his team of scientists started making boring charts, started plotting tedious dots, started doing mind-numbing statistical calculations, and the tide turned. The convoys that delivered the troops for D-Day, the fuel that powered the drive across France, the supplies that sustained the armies that liberated Europe, all of it had to cross the Atlantic. All of it was protected in part by mathematical analysis that showed escorts where to be, how to fight, how to maximize their effectiveness. There is a memorial in Liverpool, near where Blackett's team worked, dedicated to the merchant sailors who fought the Battle of the Atlantic. Thousands of names carved into stone. Young men, old men, men from every nation in the Allied coalition. They sailed into danger, knowing that U-boats were hunting them, knowing that a torpedo could send them to the bottom at any moment. They had courage, they had skill, they had determination, and increasingly, as the war went on, they had something else. They had analysts back in Liverpool, plotting courses that minimized their risk. They had escorts trained in tactics that had been proven to work. They had aircraft painted colors that science had shown were optimal. They had boring charts that saved their lives. The SS Robert Rowan, the ship we started this story with, made it across the Atlantic in March 1943. Her cargo of ammunition and tanks was unloaded at Liverpool. Her crew got shore leave, probably spent it at the pub complaining about the Navy's new orders and routes. 3 months later, the Robert Rowan was hit by a German bomber off the coast of Sicily and exploded in spectacular fashion. There's famous footage of the incident, a massive mushroom cloud visible for miles. She was lost, along with several crew members. War is like that. You can optimize, you can analyze, you can do everything right, and sometimes luck runs out. But because of the operational research that guided Atlantic convoys, the Robert Rowan made multiple successful crossings before her number came up. Her crew survived those Atlantic runs. Other ships, protected by better tactics and strategies, made it through the war entirely. We tend to remember the dramatic moments of World War II, D-Day, the Battle of Britain, Midway, Stalingrad. Those are the stories that get told, the moments that captured the imagination, the events where the fate of nations hung in the balance. But wars aren't won just in dramatic moments. They're won in the accumulation of thousands of small advantages. They're won by doing ordinary things slightly better than the enemy. They're won by people who never fire a shot, but who figure out how to get more food to the front lines, or how to maintain more trucks, or how to route convoys more efficiently. Patrick Blackett was one of those people. He didn't storm any beaches. He didn't shoot down any aircraft. He didn't captain any ships. He sat in an office, smoked too many cigarettes, filled out endless charts, and did mathematics that most people found incomprehensible and boring. And he saved 3,000 ships and 30,000 lives, and possibly an entire nation from starvation and defeat. The next time you hear someone dismiss data analysis as boring, the next time you think that statistics and mathematics are abstract and irrelevant, remember the Battle of the Atlantic. Remember that behind every data point was a ship, a crew, a cargo of food or fuel or weapons. Remember that patterns invisible to the human eye can mean the difference between life and death. Sometimes the most boring work is the most important work. Sometimes the person sitting quietly with a calculator is as much a warrior as the one standing on a pitching deck in a North Atlantic gale. Sometimes victory comes not from courage or strength or brilliant leadership, but from someone who was willing to plot dots on a chart and see the patterns that everyone else missed. That's the lesson of Patrick Blackett and the operational research revolution. Not that science replaced courage, not that mathematics replaced leadership, but that modern war required both. That the brain was as important as the heart. That systematic thinking was as valuable as brave action. In 1943, Admiral Dönitz wrote in his diary that the Battle of the Atlantic had been lost, not because of some new weapon, not because of overwhelming numbers, but because the enemy has gained the upper hand through superior organization and more effective tactics derived from scientific analysis. He was right, and the scientists who achieved that victory never fired a shot. They just made boring charts. They just did tedious calculations. They just asked over and over again, what does the data actually show? And the data showed them how to save 3,000 ships. In the gray waters of the Atlantic, in the midst of the greatest war humanity had ever fought, mathematics and careful analysis proved to be as powerful as any weapon. The man who understood this, who dedicated himself to the boring work of plotting patterns and calculating probabilities, changed the course of history. Patrick Blackett, the physicist who saved an island nation with dots on a chart. The analyst whose boring methods defeated the wolf packs. The scientist who proved that sometimes the most heroic act is simply to count carefully and think clearly. That's the story. That's the truth. And that's why every ship that made it safely across the Atlantic, every cargo that reached the docks, every sailor who came home to his family, owed their survival in part to one man's belief that behind the chaos of war, there were patterns waiting to be discovered. All you had to do was be willing to do the boring work of finding them.